So imagine you're trying to launch this incredibly heavy payload into space, right? And you look at your rocket and you realize a massive chunk of the weight you're lifting is, well, it's just a secondary engine that exists purely to pump fuel into your main engine.
Yeah, it's incredibly frustrating.
Right. And back in the 1960s, rocket engineers had what they thought was this brilliant idea to fix it. They decided to, siphon off some of the unimaginably hot exhaust from the main combustion chamber to power those fuel pumps instead.
Which, in theory, sounds great.
In theory. But the result was that they instantly melted their own engine plumbing into just a puddle of slag. I mean, they were playing with gases hot enough to liquefy solid metal, and nature won.
Big time.
Yeah. But today, we are looking at this stack of technical schematics from Firefly Aerospace. And they show how modern engineers have actually resurrected this exact catastrophic idea from the 60s, solved its fatal flaws, and completely changed the math on how much payload we can push into orbit.
And, the reason this matters, why engineers would even risk playing with metal melting gases in the first place, it really comes down to just a fundamental frustration in rocket science.
Oh, absolutely.
Because launching anything into space is, well, it's a brutal fight against gravity. Every single ounce counts. But traditional rockets, they dedicate this massive chunk of their weight to that secondary engine you mentioned.
It's the ultimate engineering irony, right? You are literally burning fuel to lift an engine that exists entirely to pump the fuel you are burning.
Exactly.
So our mission for you listening today is to really understand Firefly's integrated tap-off power architecture. But I think let's unpack the status quo first. Like, why do we even need this massive fuel pumping operation?
Well, think about the extreme environment inside a rocket's main combustion chamber. You have this continuous, incredibly violent explosion happening, which is what creates thrust. But that explosion also creates immense internal pressure. So if you try to just, casually pour fuel and liquid oxygen into that chamber, the pressure is just going to aggressively blow it right back out.
It's basically a wall of pressure.
Yeah. You have to force the propellants in at a pressure even higher than the explosion itself.
Which means you need pumps, like really, really big pump.
Turbo pumps, to be specific. And these things, they pull thousands of horsepower. They require massive amounts of energy. So for decades, the standard way to power these beasts has been what's called a separate gas generator.
Right.
Basically, you build a smaller secondary combustion chamber, burn some of your rocket fuel in there, and use that specific exhaust to spin the pump.
Okay, let's unpack this because I always visualize this as well. It's like trying to build a high-performance sports car, but to get the fuel injection to work fast enough, you strap this heavy, completely separate lawnmower engine onto the roof of the car.
That's a great way to look at it.
Right. And that roof engine drinks your main gas tank. It adds a ton of weight, and it needs its own complicated wiring and plumbing.
And the kicker is, that roof engine is actively stealing your cargo capacity.
Oh, totally.
Every pound of separate gas generator hardware is, it's a pound of scientific equipment or satellite that you just can't launch. Plus, you're adding severe complexity.
More parts to break.
Exactly. A separate engine requires heavy hydraulic valve networks to control the flow of all those propellants. More moving parts just mean more potential failure points. And then there's the soot.
Oh, right, because rocket exhaust isn't exactly clean, is it?
Far from it. The exhaust from these traditional gas generators is incredibly dirty. It's just thick with unburned carbon.
Yuck.
Yeah, and when you blast that dirty gas through your delicate high-speed turbo pump, it coats the blades, it ruins the aerodynamics, and just severely degrades the pump's lifespan over time.
So you're basically stuck with a system that is heavy, it's complicated, and it slowly destroys itself.
Pretty much.
I can totally see why engineers in the 1960s were so desperate to find a shortcut, and their theoretical shortcut was this tap-off concept, right?
Right.
The idea being, instead of building a separate gas generator, why not just drill a hole in the side of the main combustion chamber, siphon off some of that high-pressure exhaust you're already making, and just use that to spin the turbo pump.
It is the holy grail of elegant design. You eliminate the weight of the separate engine, you strip out the complex hydraulic valves, and you just harness the pressure you are already generating.
Except for the part where it turns your plumbing into molten slag.
Right, yeah. That was the unfortunate reality of those 1960s tests.
Yeah.
The source material refers to this as experiencing catastrophic turbine thermal control.
Which is a very polite way of saying it blew up.
Exactly. They were trying to route unconditioned, raw exhaust straight from the heart of the fire.
How hot are we actually talking here? Like In the chamber?
Thousands of degrees. I mean,
Yeah.
far beyond the melting point of the steel and the superalloys they use for the plumbing. The thermal limits of those metallic extraction manifolds and the turbopumps were just instantly exceeded. You simply cannot pipe that raw environment anywhere without the metal losing its structural integrity and just collapsing.
Which I guess brings us to the first massive hurdle Firefly had to clear. If you can't pipe the hot gas, how on earth do you get it to the pump?
Well, their solution is this brilliant piece of engineering called a nested manifold. So instead of just building a pipe to carry the hot gas, they built a pipe inside of another pipe.
Okay.
The inner pipe carries the superheated extraction gas, and the outer pipe, like the jacket surrounding it, is flooded with raw, liquid kerosene fuel.
Wait, hold on. I'm looking at these schematics. They are taking gases hot enough to instantly melt metal, and their big solution is to surround that exact extraction pipe with highly combustible rocket fuel.
It sounds totally crazy, I know.
Isn't that literally building a bomb? Like you have metal melting heat right next to raw fuel.
It sounds terrifying, right? You are putting the ignition source millimeters away from the explosive. But they are relying on a principle called regenerative thermal defense, and it turns this apparent bomb into, honestly, an incredibly efficient heat exchange system.
Okay, I'm listening.
Let's look at the physical state of that kerosene. When it enters the outer cavity of this nested manifold, it is highly pressurized and absolutely freezing cold.
Freezing cold. Okay, so it's acting like a liquid coolant jacket, basically.
Exactly.
But wait, if that intense heat transfers into the fuel, doesn't the fuel boil, expand, and then explode inside the pipe anyway?
See, the immense pressure of the fuel system actually prevents the liquid from boiling into a gas, even as it absorbs a massive amount of thermal energy.
Oh, wow.
Yeah, so as this freezing pressurized fuel washes over that inner tap-off manifold, it basically acts like a sponge. It pulls the extreme heat through the metal wall and absorbs it into the liquid. This continuous flow of cold fuel guarantees the metal manifold never actually reaches its melting point.
So the heat just passes right through the metal and into the moving fuel.
Precisely.
And I guess every pound of metal they don't have to use to artificially thicken or, reinforce that pipe to survive the heat is another pound of payload you get to launch.
That is the constant underlying math of rocketry. But the brilliance of this doesn't stop at just preventing a meltdown.
There's more.
Oh, yeah. The fuel, which is now significantly heated from its journey around the manifold, it doesn't just sit there. It gets routed downward into a series of cooling channels that run the entire length of the thruster body.
So they are actively using the extreme heat to perform a completely necessary function.
Yes, and they get a huge performance boost out of it, too. By preheating the liquid fuel using the exhaust gas, they actually increase the combustion efficiency of the main engine.
Because it burns better.
Exactly. Warm, energetic fuel mixes and vaporizes much faster and burns far more completely than sluggish, freezing cold fuel. They literally took a fatal thermal hazard and turned it into an engine upgrade.
That is so cool. It completely flips the script. Instead of fighting the heat with heavier metals or weird ceramics, they just relocated it to where it makes the rocket fly better.
Yep.
But, I mean, preventing the metal from melting is only half the battle, right? Because you can't just suck any random pocket of gas out of a rocket combustion chamber. It's got to be totally chaotic in there.
Oh, it is an absolute inferno. You've got varying temperatures, unburnt pockets of fuel, and wildly different chemical mixtures all swirling around.
And from my understanding of turbopumps, if you hit those delicate, high-speed spinning turbine blades with erratic, unpredictable gas pulses, you'll just shatter the whole assembly.
You destroy it in seconds.
Right. So you need a highly specific, steady, oxygen-rich gas mixture to run the pump safely. How on earth do you reach into a literal firestorm and pull out exactly the specific mixture you need?
You use fluid dynamics.
Fluid dynamics.
Yeah. Firefly's engineers didn't try to build, physical scoops or complex moving mechanical valves inside the chamber to sort the gases.
Because those would just melt or break anyway.
Exactly. Instead, they manipulate the flow of the propellants themselves using a technique called cross-impingement.
Cross-impingement. Okay. Let's visualize how they set this up inside the chamber for everyone listening.
Okay, picture the top of the combustion chamber, the injector head. They pump the liquid oxygen, the LOX, straight down from the top, injecting it parallel to the outer wall.
Okay, straight down.
But the kerosene fuel is injected horizontally, coming in straight from the side ports on the wall.
So you have this vertical stream of freezing oxygen and a horizontal stream of fuel, and they are colliding violently at a perfect 90-degree angle.
Yes.
When I read this in the source material, first thing that came to my mind was like a high-speed salad spinner. Centrifugal forces immediately take over.
That visual actually holds up perfectly against the physics at play here. In fluid dynamics, that specific perpendicular collision at the top of the chamber creates what is called a toroidal vortex. Yeah, toroidal just means donut-shaped. So imagine a violently spinning ring of gas and liquid, just constantly churning right at the top perimeter of the chamber.
Okay, I have the donut of fire in my head. But how does a spinning donut of fire help us sort out the specific oxygen-rich mixture we need for the pump?
It comes down to density and centrifugal force. As that vortex spins at incredible speeds, the heavier elements in the mixture get pushed outward against the chamber wall, exactly like the water getting flung to the outside of your salad spinner.
Wait, what makes the oxygen heavier than the rest of the fire? I would think the combustion gas is heavier.
It's about the state of the molecules. The liquid oxygen being injected is incredibly dense.
Oh, because it's still liquid.
Right. Even as it begins to vaporize and mix, those uncombusted oxygen molecules are significantly heavier than the extremely hot, rapidly expanding exhaust gases that are produced by the combustion happening toward the center of the vortex.
Ah, I see.
The lighter, hotter combustion product stays central, while the dense, cooler, oxygen-rich boundary layer is physically pinned against the outer wall by that centrifugal force.
That is wild. They are literally using the spin of the collision as a giant centrifuge to separate the gases.
And because the physics of that vortex are constant, as long as the engine is running, Firefly knows exactly where that oxygen-rich layer is going to live.
It's always in the same spot.
Exactly. It is reliably plastered against the wall, just below where those propellants collide.
Yeah.
So to get their perfect gas mixture, they simply place their tap-off extraction holes directly below the horizontal fuel ports.
They just put a bucket exactly where they know the good stuff is going to fall. They don't need a mechanical separator at all.
It is entirely passive. It requires 0 moving parts.
Wow. Okay, so we've kept the pipe from melting using the nested manifold, and we've successfully isolated our steady stream of oxygen-rich gas using the toroidal vortex. We should be ready to power the turbo pump, right?
You'd think so.
But reading through the schematics, there's still one lingering ghost from the 1960s, designs the soot.
Yeah, the soot is a major issue. Even an oxygen-rich combustion gas carries unacceptably high levels of carbon soot. And if you recall the problem with the old separate gas generator engines, soot is just the ultimate enemy of efficiency.
Right, because pumping heavy soot through a turbine that is spinning tens of thousands of times a minute is essentially like sandblasting the delicate blades. It ruins the aerodynamics and kills the engine's lifespan.
Exactly. If you were trying to build a reliable rocket, let alone a reusable one, soot is a total death sentence for your turbopump.
Well, here's where it gets really interesting for me. I saw Firefly's solution for this, and honestly, it sounds even more unhinged than wrapping a hot pipe in raw fuel.
It really does.
Their answer to having too much soot in the gas is to intentionally start a second fire inside the wall of the engine. How does starting another fire clean the smoke?
I completely understand the skepticism. Usually, more fire equals more soot. But the secret lies in the chemistry of how this specific secondary fire burns.
Okay.
The source details a mechanism called the tap-off fin, which triggers a process they call flameless mode. It happens in a 4-step micro-injection sequence. Let's break down the chemistry.
Yes, please. Walk me through step 1.
Step 1 is atomization. Remember that cold fuel we used to cool the nested manifold?
The sponge fuel.
Yeah, a tiny fraction of that fuel is forced into the tap-off pathway through a precisely milled elliptical port. Because it's being squeezed through this very specific shape under immense pressure, it atomizes. It turned into an incredibly fine mist.
Like a high-end perfume sprayer, but with rocket fuel.
Exactly like that. And then step 2 is evaporation. That fine mist of raw fuel is injected directly into the tap-off pathway, which is already filled with the hot, oxygen-rich gas we just extracted from the vortex.
Okay, so it meets the hot gas.
Yep. The intense ambient heat instantly flashes that liquid mist into a vapor. It evaporates completely.
Wait, really? It just instantly turns to vapor?
Instantly. So now we have evaporated raw fuel thoroughly mixed with the hot, oxygen-rich tap-off gas. And that brings us to step 3, which is flameless burning.
I have to admit, this concept tripped me up. How do you have a fire without a flame? I always just assumed the flame was the fire.
It's a super common misconception. When you look at a traditional flame like a candle or a campfire, you're seeing what's called a flame front.
A flame front.
Right. That is a distinct, relatively thin boundary layer where the fuel and the oxygen are finally meeting and combusting. But the problem with a flame front is that the mixing is imperfect.
Meaning not everything burns.
Exactly.
Mm.
Pockets of fuel burn without enough oxygen, and that incomplete combustion is what leaves behind unburnt carbon. And that is what soot is.
Oh. So a visible yellow flame is basically just a visual indicator of a dirty, inefficient burn.
Precisely. But inside this tap-off fin, the conditions are entirely different. Because the fuel was completely evaporated and thoroughly pre-mixed with the abundant oxygen before it ignited, the combustion doesn't happen at a distinct, messy flame front.
Where does it happen?
It happens everywhere, simultaneously within that entire volume of space. It sparks a volume-distributed, flameless burn.
Wow. The reaction is so perfectly mixed and uniform that it burns completely clean. There's literally no unburnt carbon left behind to make soot.
Which gives us step 4, clean exhaust. The output of this flameless mode is a totally soot-free, near-ideal gas.
That's amazing.
It is perfectly calibrated in both temperature and chemical makeup to spin that delicate turbopump at absolute maximum efficiency without leaving a single trace of residue on the turbine blades.
It's just incredible. I mean, they solved the thermal destruction, they solved the chaotic mixture control, they solved the exhaust soot. But taking a step back from the individual mechanisms, the thing that really stuck with me from these sources isn't just the ingenuity of these 3 distinct solutions, it's how they all completely rely on each other. None of these are independent, bolt-on fixes.
No, they form a unified flow architecture. It is a masterpiece of thermodynamic looping.
Let's actually trace the path of a single drop of fuel to see how this all connects. We start with the freezing cold fuel entering the nested manifold. Its first job is acting as a coolant absorbing heat so the extraction pipe doesn't melt.
Right. And as it absorbs that heat, it becomes pre-warmed, highly energetic fuel. It then flows down the exterior wall channels, providing necessary regenerative cooling for the rest of the engine bell.
Right, and as it flows down, a tiny sliver of that warmed fuel splits off at the tap-off fin. It goes through the atomizer, evaporates, and triggers the flameless burn that cleans the soot out of the tap-off gas.
Meanwhile, the bulk of that fuel continues its journey down to the bottom of the engine, loops back up, and shoots horizontally out the side ports into the main chamber,
where it violently smashes into the downward-flowing liquid oxygen, creating the spinning toroidal vortex.
And that vortex centrifugally separates the gases, pushing the critical oxygen-rich boundary layer directly into the tap-off openings, feeding the exact mixture needed to sustain the entire cycle.
It's poetic, almost. The fuel isn't just a propellant. It's the manifold coolant, it's the engine bell coolant, it's the catalyst for the soot-cleaning secondary fire, and it's the physical kinetic force that creates the sorting vortex. Every single component is solving multiple problems simultaneously.
Which brings us to the ultimate question for anyone listening today. Why does this matter? Why should you care about this elegant loop beyond just appreciating it as a cool piece of engineering?
Right, because of the payload dividend. It comes all the way back to what we talked about at the very beginning, that brutal fight against gravity.
Exactly. Firefly's architecture fundamentally rewrites the math of orbital propulsion. They achieve 3 massive dividends.
Lay them out for us.
First is structural efficiency. By completely eliminating the secondary gas generator and tearing out all those heavy, complex hydraulic valve networks, they drastically reduce the dry mass of the rocket.
Meaning the physical weight of the hardware itself before you load the fuel.
Exactly.
They basically took the heavy secondary lawnmower engine off the roof of the sports car, and every pound of dry mass you remove from the vehicle translates directly into an extra pound of actual payload you can put into orbit.
Exactly right. Second is operational reliability. Whenever you remove interconnected, active parts, you reduce your potential failure states. Mechanical valves can get stuck, complex plumbing can burst. But a toroidal vortex created by fluid dynamics, physics doesn't get stuck.
Physics doesn't get stuck. I love that.
Yeah, as long as the pumps are pushing propellant, the fluid dynamics simply happen.
And the third dividend ties back to the soot, right?
Yes, the extended lifespan. Because of that flameless volume-distributed burning, the gas hitting the turbopump is pristine. It protects the structural integrity of those crucial turbine blades across the entire flight envelope.
Lift off to orbit.
From the second the engines ignite on the launch pad, through the immense vibrations of breaking the sound barrier, all the way into the vacuum of space. You aren't sandblasting your own equipment. The engine becomes robust, reliable, and fundamentally reusable.
Man, We started this deep dive talking about a spectacular failure from the 1960s. Engineers tried to simplify rockets and ended up melting them. But what Firefly has done here is resurrect an abandoned dream, not by adding more complex machinery or heavier valves, but by cleverly routing the fuel they were already carrying and just letting fluid dynamics and thermodynamics do the heavy lifting.
It is a total paradigm shift in how we approach complex systems.
Yeah,
And I think it leaves us with an important, really provocative thought to consider in our own lives.
I like where this is going.
Well, Firefly succeeded because they utilized fundamental passive laws of nature rather than relying on active, breakable, heavy-moving parts.
They stopped fighting the environment and started using it.
Exactly. So look around at the technology you interact with, or the systems you work with professionally. Where are you relying on heavy, complex, failure-prone valves, whether those are literal mechanical parts, bloated software processes, or even overly convoluted management structures?
Right.
Where are you forcing a complicated active solution when you could design a system that allows the natural flow of a process to simply do the work for you?
Where is your secondary engine on the roof, and how can you design it out of existence? I mean, that is a fantastic question to leave off on. Thank you for joining us on this deep dive into Firefly's tap-off architecture. Keep questioning how the world around you is engineered, and we'll catch you on the next one.